Problem number 6, electro-hydro entanglement, asks us to explain the analogy that is often made between electric and hydraulic circuits. We must answer where that condition, where that analogy is consistent and where not. And also it asks us to describe elements of electric circuits through counterparts in hydraulic circuits. So, the analogy, basically the current in an electric circuit can correspond to the flow rate in a hydraulic circuit, and the voltage to pressure. In an electric circuit, you have electrons moving in the material. In hydraulic circuits, you have fluid mass moving in that in tubes. So, a thin hose can be used a thin hose has an analogous function to an ohmic resistor. A source that corresponds to a water pump, and a switch to a valve. There is a law. There are two similar laws connecting flow rate and the difference in pressure. And in the electric circuits, there's a similar expression between current and voltage. Resistance, which is the constant correlating those two properties, has an expression given by that formula in its circuit, and Kirchhoff's laws apply for both circuits. Although the analogy stands, holds ground, there are some cracks even from the very beginning. You see that there is a different geometrical law for the resistance and in flow rate and in current. That means that, for example, if you double the cross-sectional area of a wire, the current will double. But if the same happens in a tube, the flow rate will quadruple. Also, the temperature has an opposite effect on the two kinds of circuits. That's because they are both analogous to the resistance, the resistivity and viscosity. There are different temperature laws regarding the.
So, when you start to consider circuits, you should consider on how the initial movement is conducted. So, if you have a DC circuit, that's the analogous for this is an electrical or a pump with a definite input and output gates. If we want to replicate an alternating current source, you need an oscillating piston that is inside the tubes and starts to oscillate, and along with this, the whole fluid inside the circuit. We need to point out though that the frequency of the piston should be sufficiently low so we don't have waves inside the propagating waves inside the tubes due to the finite speed. So here we see an analogy for the capacitor. It's a piston connected with a spring which is stable, And as we have no current flow, it blocks completely current flow in DC like a normal resistor, normal capacitor does, and it holds a certain amount of energy in it, which can be produced, from which we can produce current. In an AC circuit, the flow is not exactly flow. An oscillation in the liquid can be actually visible. Even if we have a capacitor, it's like having actually an alternating current. So, for inductor, we use a turbine which has a considerable mass and which, due to its inertia, will react to any atom to change the flow. And an ideal turbine will not influence the flow. It will just provide enough inertia in order to have some inductory effect on the circuit. Yes, and the energy, instead of magnetic, is stored as kinetic energy. So, okay, now we have another difference we have is when the circuits are oscillating, there is no the circuit has its own natural frequency, and it can respond to different perturbations with different amplitudes in oscillations. So, we can be able to construct our water radio. We have the transmitter and the receiver. The transmitter has an RLC analogous system with an alternating current, an inductor and a capacitor. These two are magnetically coupled, and it's a cord with a magnet on top of it, so it would follow the oscillations of the own source. So the waves propagate on the liquid and are picked up by the same setup, where also we have two coupled magnetic source and the receiver. So that's a way where we can induct our own, we can propagate our information from that circuit to that circuit. And what about the resonance? How can we tune our radio? We can add a rubber band that changes actually the elastic constant of the spring of the capacitor, which we can have it to be harder to push or lighter. Well, we can have an area in which we can tune the natural frequency of our radio and have amplitude to be amplified. So another breakdown of our analog is that we have no magnetic field, and because of that there is no time delay of the flow, because that would lead to breakdown of the mass conservation here. The flow will not be continuous. The two distinct fluid circuits cannot be coupled because there is not such a magnetic field, and the inductor we have proposed works directly and not through an indirect magnetic black field. So, a semiconductor could easily, a semiconductor can be considered as essentially water, being a semiconductor, because if we freeze it, if we keep it low enough temperature, it freezes and we don't have flow. And liquid helium could be the substitute for superconductivity because it has no viscosity and so there is no resistance in flow. And there is a similar mechanism behind the phenomena is the Bose-Einstein condensations. So here we can see a diode, which is a one-way valve. Here we can see something like a transistor. So this is a spring. We have an incoming flow. The flow turns due to internal flaps, turns the outer cylinder and uncovers some holes which analogous with the flow in this tube, produces a larger flow on the whole tube. So that could be an amplifier transistor. And we have also logical gates. Here is the XOR gate, where we can see that satisfies all of the three logical relations on our circuit. And we also have an AND gate. which also applies the flow, the logical relation between the circuit parts. What we should say is that with the combination of those gates we can also make binary additions. So one should start after this, could consider looking at more complicated systems such as the our hard flow rates.
Okay, thank you.
Yes, I would like to see slide 11, please. Yes, so you say there is no time delay response.
Well, I'm Åke from Sweden, and I will be doing the session on grid problem 15, electro-hydro entanglement. And I would like to thank you for your theoretical work on this problem. And I will so I will just reiterate the problem descriptions. We have I've highlighted to state the conditions, which is the main question of this problem. And then there is a list of components that we could try to make. And then it's highlighted, it said, try to create and demonstrate. So my interpretation of this is that you should state the specific analogy for when is it applicable. You should try to translate some electric components into hydraulic ones. And you should verify your theory with experience. Now, starting with the good points of the slide, you had a very consistent analogy. You always kept to the volume and the pressure, which is good. I would have liked to see a bit more clearness on what pressure, but that's a side point. Then you showed that the Kirchhoff's law was fulfilled, which I think was very important because we use Kirchhoff's law to prove many things in our electrical circuits. So now that we have shown that hydraulics satisfies Kirchhoff, we can repeat the same proofs. So that's a very great addition. I think that's one of your strongest cards. And also you compare Ohm's law with Poiseuille's law, which I agree. They are similar, and you also looked at the differences, the difference of radian, and possibly you could have talked more about the implications of thin tubes and such. But I think it was a good eye to find the differences there. There are some, and here's a list of the components to consider. You consider the AC/DC source, which I think was good. The capacitor was excellent. The inductance, I disagree with your construction, and I will return to this topic later. You had the resistor, and yeah, you had pretty much all of the components. And you also showed us an oscillator and a radio receiver and a superconductor. And I would like to point out that the superconductor works for superfluid helium, which is not really the same as liquid helium. It's the lander point. But I get what you were trying to say. Now, some improvements for the theory is that, well, the pressure, you should tell us, is it a static or stagnation? Because that greatly affects what a conductor is. And you didn't discuss the alternate analogies. So here, you can choose the static, you can choose the stagnations, but there are some differences that you must take care of. And therefore, you only looked at one, and you didn't actually specify. So I would like to be more clear about that. You did not state the conditions of Poiseuille's law. And this problem, in the description, it says, state the conditions. That's the problem. And you did not state the condition. For example, Poiseuille requires laminar, fully developed flow in a straight tube. You only said, well, it holds. And later you specified for cylindrical flows. But what's really important here is the laminar flow. Because the question asks, what are the limits? And laminar flow is limited, or at least indicated, by the Reynolds number. By the way, which I saw no mention of. So there was some dimensionless number lacking. For example, the Reynolds number for making Poiseuille work, and the Ohnesorge number plays into this when you try to create very, very thin conductors. Then when the size of the tube gets less than the size of a water droplet, then you will start seeing some different behaviors. And also, you said that when I applied a pressure on one side in a conductor, it would immediately start moving. This is false because of Newton's second law. If I push something, it doesn't immediately get velocity. It accelerates. And water has mass. And therefore, every tube has a self-inductance that is proportional to the density of the fluid. And this statement is simply, you take Newton's second law, and you divide on both sides by the area. Then you get a pressure and you get a volume flow. And experiments, well, there were no experiments, and I think that was something that was lacking in this presentation. You should have done something to verify. I think you had some impressive schematics of components. I would have liked to see some of them realized, and maybe you could have compared the experimental results with the predicted theory from this analogy. Just a suggestion. So my discussion points is first the choice of potential, whether it's the static pressure, the stagnation pressure, or even something else. Then I would like to ask, what's the scope of your study? What have you added? Because if I just Google electro-hydro analogy, I get to see all these components in 10 minutes, and I acknowledge that your schematics of logic components were something that you made yourself, and they were they intrigued me. So, but I would like to know more specifically.
Okay, that's the discussion.
Yes, I would like to know more specifically.
The discussion starts. Yeah.
Yes, I'm just continuing speaking the point. I just wanted to know what is your addition to this precisely, and then in the finishing, I would like to actually answer the question: when does the analogy hold? So what's the limit? So beginning with the choice of potential.
Can you rebuild the previous slide? When you say static and stagnation pressure,
Yes.
what exactly do you mean?
Okay, so let me show an image. Maybe not that one, but here. Let's draw a pipe. And let's have it become wider. So the static pressure is simply if we would make a water column here and look at the height, then the height will be proportional to the static pressure. And
I believe I got what you mean. All of the schematics are drawn on a plane, XY plane. We don't have a vertical.
Well, it's not the height really that's important. So the difference, this is the T static. The stagnation pressure differs by if you would have a kind of straw that points in the direction of the flow and goes up like this, then you would measure a higher stagnation pressure. And in fact, I believe these are related by the P stag is the half rho of P squared plus the P static. So you can choose either one of these. But the reason I'm asking is that, okay, first of all, which one do you choose?
It's the stagnation.
And I think that's good, because when we move over to this pipe, then the static pressure changes.
You need to check the pressure on a vertical dimension, on a vertical plane on the flow. How, if you put your hand on the flow, how much pressure will you feel? It's that kind of pressure.
Yes, so that's a stagnation pressure. But I prefer to use this pitot probe instead of my hand. And I would like to point out that when you have choose this, then if the pipe gets broader, the stagnation pressure is conserved. So that makes this a conductor. However, I would also like to talk about slopes like this. So with your potential, the pressure will be higher here, correct?
Well, no.
That's an XY plane. We have no.
So you did not take the height.
Because
okay. Then I see. I had a point about this, but I respect that you chose to work only in the horizontal plane, and I will drop this point.
Okay. Also about your mention about the Newton's second law.
Yes.
What we said was not only just adjusting the pressure on one side, but on both sides. So as the fluid moves like a continuous medium along the tube, due to continuity reasons, it's not possible. If you adjust the pressure on both sides of the tube, then you can get that kind of continuous movement.
Okay. I would like to move on to point that 2. So what is the scope of your study? I know that you created the schematics yourself. What else did you do yourself?
Okay. About the limits of the analogy.
no, point 2.
Oh, I'm sorry.
That's
Scope of the well, as you said the logical elements and the contributions are some contributions that are not obviously stated in bibliography, but also about the other elements imposed where we can say we can find it easily. In fact, there are mistakes. For example, you said you have a problem with our inductor.
Yes.
Okay, it is a fact that assuming that continuous flow I was talking about, and having an inductor along the flow, if you move a continuous medium, elastic flow, it would immediately rotate the inductor. In fact, what you need to do is have a little space below the inductor so that the flow is conserved.
Yeah.
That's some space.
Also, but given this new knowledge of the self-inductance of a tube, I would propose another. You could just take a tube and have a really long but thick tube. Then it would have. You could have just like take a tube and you just make several loops of it, like a coil. It's actually a coil.
But there you assume a finite speed. You assume that the speed of.
I'm assuming the speed of water is finite.
Yeah. We haven't measured frequencies where that's important.
Excuse me, we'll continue later. Now let's just give the word to the U team.
Okay, we didn't get well. Did you? Hello, ladies and gentlemen. My name is Alexandra. I represent the team of the Russian Federation. I'm going to present you our review to problem number 6. Now let's start with the review of the report. The report was, well, it was just following the statement of the problem. So report said something about the analogy between some electric things and this in hydrodynamics. Then he made a simple circuit. Then he kind of tried to estimate the limits of his analogy using the slide with the breakdown. Then he talked a little about the AC and DC. Then he made a scheme of inductor, a scheme of radio, which I think won't work because it's not ideal. Then he kind of told us about the magnetic field, but I don't agree with every point of that. And then he talked about semi and superconductor, and there was no clear explanation of semiconductor, but with superconductor it's okay. Then he made some triodes, diodes, and logical elements, like logical OR and logical AND. But logical OR, I think, will be actually an exclusive OR because of some... Yes, it was exclusive. Oh, sorry, exclusive. Yeah, sorry. And now let's go to the opponent. Opponent said that reporter had to do according to the task. He started with that. But he didn't retell the report. But it's okay because report was just as the task. Then opponent said about something at good points and improvement, like they reported in static conditions and limits like laminar flow, turbulent flow, and that report did not any experiments, which is actually bad. And opponent did a good job, but in discussion he was mostly like a teacher and explaining to the reporter some things about the pressure. Now I understand which pressure is here. And I don't think that that the question about the scope of their studies was really relevant, but I like the third question, and I think we will start our discussion with that. And as I think reporter did kind of good theoretical work, but these schemes are for really ideal situation, and reporter did what the task asked and not something like behind this task, which can be interesting. If we will have time, we will discuss it. And opponent did quite well, but in the discussion he was mostly like a teacher. So now let's go to the first question, which is like laminar flow, turbulent flow, and the limits of these schemes.
Yeah,
This analogy.
Yes.
So, your opinions?
So again, we could use the formulation of my third point. So the question I raised on my third point, actually I can plug it in, it was what are the limits of the analogy? And this is the central problem statement. State the conditions under which the analogies work. So I would like to know, you have done a theoretical work, and I respect that. So then in terms of theory, what does your theory predict that the Reynolds number should be for your components to work?
Reynolds number.
Yes.
I believe if we consider a fluid to be like when you study a circuit, in general you don't look for the resistance of the cables. You ignore them. In such manner, you could ignore viscosity of the liquid. Because it's like when you're working with circuits, we are basically working with superconductivity through the
The
cable.
resistance is located basically in the resistance, where the
So I don't think that the material properties are quite irrelevant, because when you have a resistor, you at least look at the power rating to make sure you don't burn it off. So you should look for what Reynolds number does this hold.
I think there is
Okay, yes, it's true that the Reynolds number does not.
So again, are you familiar with the Reynolds number?
Reynolds, we don't want high viscosities, so the Reynolds number should be large.
Could you write